is not a place that you need to submit, but if you have submitted it, we will handle it to move. So hopefully by now everybody knows where to submit. Any questions about anything? Bureaucracy, material, anything? Perfect. Let's continue with the stable marriage algorithm. So we went through these slides. The input to this problem is a list of n males, a list of n females. There are each participants provide a full ranking of the opposite gender. So every male give a ranking of his preference, stating that he would like to marry female 3. If she's not available, he would like to marry female 2. If she's not available, marry female 5, and so on. And it takes a full list. And similarly, female 1 is saying that the male she would like to marry is male 3. If he is not available, then male 5, and so on. And we defined last meeting what is the notion of rogue couple, of unstable couple. So to tell you what is an unstable couple, we first need to think about some matching, some marriages or some engagement or some agreements that happen already, and now there is already some partition into pairs, males, females, and when we are looking at this partition, we look at one particular female, one particular male, which are not married to each other, and asking, are there any dangers that they have interest to break their marriages? And thinking about it as economical state, nothing, not addressing moral issues here. Thinking about it as economical state, we think about this couple of male-female as an unstable rogue couple if the following happens. Under this particular matching, one of them, say Zod, is currently married to Avanora, who is number 6 on his list. But he would much rather marry Arcadia. She's number 3 on his list. And on the other hand, Arcadia herself, she married to number 5 Syndrome, but she would much rather prefer Zod because he's higher on her list. And the instability here is that if they will break their marriages and marry each other, both of them would upgrade in their list. Both of them will go higher. So that's what made them a rogue couple. So to check when we see the matching to see if there is any rogue couple, we need to essentially pick every one of the n square pairs of people not married to each other and ask, are there any danger that they would prefer each other over their spouse? And the way that stability is obtained in a matching, what would be a matching which we'll call stable, is one at which possibly everybody gets his or her first choice and everybody's happy. That's great. But even if this doesn't happen, it can still be stable according to this definition if the following happens. It's possible that Zod would marry Avanora, but he prefers Arcadia. However, Arcadia would prefer somebody that she's preferred over Zod. That is, Arcadia would lose from bearing her marriage and marry Zod, or the other way around. If one earns, the other one will lose. There is no couple that have the interest to break the marriages and marry each other. So we will define pure definition. A stable marriage is a marriage of everybody, and males and females, such that there are no rogue couple. There is no such couple with this interest. And what we are going to study is how to find such a marriage, if possible, and how it is related to an old and not particularly successful algorithm that people used in the 1950s that was bad for many aspects, including that, however, it leads to some various stability. So, the study of stability will be the subject of this lecture, and we will see this relationship and study a few properties of an algorithm that is called the 1950s dating, or the traditional marriage algorithm, or TMA for short. So, input for our problem, a set of preferences list. Each person rank the opposite gender, each one of the opposite gender. Okay, and now given this input, we want to ask, is there always a stable pairing at all? Is there any pairing any matching that is stable according to this definition? And what will show that yes, no matter how crazy or strange the preference list, they might be consensus, all think the same thing, there might be different, doesn't matter one bit. We will always find such a matching, and the way that we'll prove the existence of such a matching would be by presenting an algorithm that finds it. And this algorithm will be actually quite fast. Of course, we can check each one of the n factorial many matchings that you can generate between n males and females. Check each one of the n factorial matchings. We would like to go for something much faster. So here is a terminology that is taken from the traditional matching algorithm TMA. So in this matching, supposedly, allegedly, each male during the matching period was going to standing next to the balcony of a female he admires and was proposing to her. And according to this algorithm, what she can do is say she can reject this proposal. She can reject this proposal and tell him, I will never marry you. On the other hand, at this stage of the marriage, this stage of the algorithm, she is not saying yes. So the only two answers that he can give is either maybe or absolutely not, but not yes at this stage. So during most of the process, a female would either not accept the proposal, or telling him maybe, which is called, we'll think about it as putting this male on a string, and this male cannot change his mind. What happens in this algorithm, he must come back in the next day and repropose once again, asking the next day what she thinks. And presumably, he might compete with other suitors that come up with the same proposal. Okay, and how is the algorithm goes? Then once a male got a no as an answer, well, to start with, the male who will Zod make a proposal first, he will make the proposal to the one that is on the top of his preference list. So he will start by making a proposal to Allegra, and the first day Allegra might say maybe, come back tomorrow. The next day she'll say maybe. At some point he might get a negative answer, and at this point he will cross out Allegra from his list, and then the next day he will go and make a proposal for the one which is a second on his list, and so on and so forth. So once Beatrice tells him, absolutely not, I will never marry you, there is no point of coming back, so he will move down the list, and so forth. So the general picture in the afternoon, there are all the worshipping males standing next to the balcony of the one they admire, and she's picking one of them and putting him on a string, telling him, come back tomorrow. And to everybody else, she said, absolutely not. I will not marry you because I already have somebody on a string. And it's kind of obvious which of these people she's going to give she's not going to put on a string. It's basically the one out of all these people, she will pick the one that is the highest on her list out of all these people, and only the ones that are proposing to her. And the catch of the algorithm is she is not contacting any of the other males, only the one that came and proposes only to this male. She is putting on a list because she already have an offer, and he cannot change his mind. Remember, he has to come back tomorrow and make the very same proposal. So in the whole algorithm, the algorithm consists of two stages. In the first stage, we have a sequence of days. At each day, it's a morning. Each male proposes to the best female, the highest on his list, that he did not cross out yet, did not reject him yet. What happened at the afternoon? Each female to today's best offer, according to her list. Of course, her list might be different than others' list, but according to her list, she will, to today's best offer, she'll say, maybe come back tomorrow, putting him on a string, and all other proposals are rejected. And it's the evening, each rejected male crosses out the females that rejected him during the same day. And we are keeping on with this process until what? Until each and every male is on a string, is on a maybe. And at this point, the algorithm moves to the second stage, and every female marries the last male that she just said, maybe, the one on the string. There could be only one per female. And our first observation here is emotional price that happens, and there are states, changes that happens to the male and the females. It might look very different and might look very unfair. So the lemma that we'll call the monotonically improving lemma will say that once one of the females have one male called B on a string, then whom she will marry? She either marry B himself, or she will marry somebody that she prefers over B. That is, the first time that she has somebody on a string, she will either marry him, or she will marry somebody that she prefers. Why? Because possibly she gets to the last day and she still have B on the string, or she rejected B because now she has an offer with B prime and she prefers B prime over B. So at this point she tells B prime, now you're on a string and B is rejected. And she'll only let go of B prime because B double prime, which she prefers over B prime, made an offer to her, and so on, and then she has ones on a string. So in this sense, her scenario is getting better and better. The one that she has on a string, once she has one, her scenario is getting better and better. Okay, on the other hand, if you think about the males, their motion price on their steps is that each male starts keeping his hope at the top of his list, and then he's getting rejected. So it looks unfair, and it's indeed unfair algorithm, but not to the direction that you think. Next corollary. Each female will marry her absolute favorite of the males, up among whom, not among all the males, or not necessarily among all the males, but how do I turn it off? not necessarily among all the males, but among the males, that ever visited, that came to propose to her. Out of all of them, she will marry the best one on her list. Okay, lemma. If the number of males and females are equal, then no male can ever be rejected by all the females. Maybe make some of us uh, give some hope. So, proof by contradiction. Let's suppose that a male B is rejected by all the females. What happened at this point where he's rejected by all the females? What the previous lemma showed us is that once one of the females have a male on a string, she always have one on the string, and it cannot be the same male, right? So each female must have one suitor at this point, B prime, because this poor guy B, why is he get rejected? Because each one of the females have somebody else on a string at this point, meaning that we have n females, each one has somebody on a string, never the same guy, some guy B, and B is not any of these ones because he was rejected by all the males, meaning that there should be n plus 1, at least many males, which is a contradiction. We said that it's the same number. In other words, this process must terminate eventually. So, how fast can it terminate? The claim is that there must be the number of days that it will take until the algorithm terminates is at most n square. Okay, after at most n square many days, and males and females, after at most n square many days, the process terminates. How come? Because every day at least one male is rejected by one of the females. Why? The algorithm stops the moment that nobody is rejected. And how long is the total length of the preference list of all the males? Each male has a preference list that contains n names, and so the total length of all these lists is n square many names, and at each day one of these names is crossed out, possibly a few at the same time. So after at most n square many days, the process must terminate. There could be at most n square many rejections, if you don't want to think about the days, just about a computer implementation. After at most n square many days, the process must terminate, and we'll get to stability. Okay, any questions so far? Okay, so there is an algorithm, TMA. It produces some kind of matching, pairing one-to-one. How do we know that it's stable? Remember, we said that stability, said that the TMA obtain a stability T if there are no rogue couples. Let's remind you what is a rogue couple. So Zod and Beatrix, not married to each other, forms a rogue couple because Zod is married to Evandora and he prefers Beatrix, while Beatrix is married to Syndrome, but she prefers Zod. Okay, and at this point they might break their marriages and marry each other. So at this point I was planning to ask you guys, but I don't see how to break you into rooms, so just take a moment and tell me why such a pair will never happen during the TMA. So
Because females pick their top choice, and so by definition, if they picked anyone else, they would be losing out.
It's not clear that anybody here will get his or her first choice. It's possible, maybe I can prove that one of them will, but in general, if all the males have exactly the same list, if they rank female in the same way, then only one of them will get his or her top choices. So my question to you was, I showed you what a rogue couple is. It's again, couple not married to each other. Well, they are married to other people, but they prefer each other over the couples. And the marriage, the decision that Zod is married Avanora is made based on the TMA algorithm, and so that, and the same for Beatrix. She's married Syndrome because of the TMA, the same algorithm. And my question to you is, could it be that this will be an output of the algorithm? By the way, I was looking for names of some of the names. I was looking for mean characters, so and was trying to make sure that I will not hit anybody that you know by mistake. That's how come Zod and the N syndrome appear there. Even though syndrome was not really bad, but syndrome is indeed from The Incredible. So we get one of the references. Other references. So syndrome is indeed from The Incredible. Maybe it's a Shakespeare, I'm not sure. Yes, I mean, you are right. Zach, you are sure about the Shakespeare? Yes. What about Gus? Yeah, that was easy. That, of course. Okay. So yes, there is something about the way of the choices, of course, because let's see the proof. So let's assume by contradiction that male 2, which will be Zod in this case, second one on Beatrix list, and female 1, Beatrix in this case, is an example of a rogue couple. So M2, namely Zod, prefers Beatrix over his wife, F2, Avanora. So we want to claim that Beatrix prefers her husband over Zod. And why is this? Because what dictates the order of the proposal that Zod made? Zod made his proposal based on, he started with Allegra. She was his top choice. and he wouldn't make the proposal to the second choice before Allegra rejected him. Only when Allegra rejected him, he went down to this anonymous person, and when she rejected him, he made a proposal to Beatrix. We assume that he prefers her over her wife. And why did she reject him? He preferred Beatrix over his wife, but she has rejected him because she has somebody that she prefers over him. The only reason that she was, based on the algorithm, the only reason that Beatrix would have rejected him is because she has somebody that she is prefer over Zod, Mr. Byrne in this case. Which means that, does it mean that necessarily she will marry Mr. Byrne? Well, here she doesn't have anybody that she prefers over Mr. Byrne. The previous lemma told us that maybe there was other people that she preferred over Mr. Byrne that proposed to her, but all of them, if she dropped Mr. Byrne to marry somebody else, then it's definitely this somebody else she prefers him over Zod. So in particular, the Zod must be below syndrome, not above him. That's what this arrow tries to say. Right? Going over the proof, during the TMA, Zod proposed to Beatrix before he proposed to F2, to Aventia, and at some point Beatrix F1 rejected Zod, FM2, for somebody that she prefers, and the monotonically improving lemma guarantees that whomever she has when the algorithm terminates, she prefers him over Zod. So maybe he prefers her over his wife, but she definitely does not prefer him over her husband, and hence the stability. Okay, so we know this algorithm, at least not judging if it's good or bad, but definitely it will yield a stable marriage, that is a rogue-free marriage outcome. It will take, as we said, n-square rejections. As a trivia, I was debating if I want to go into the math of it, but as a trivia, is this good for the males? Is this good for the females? How do we compare it? We saw the males are getting better and better. The males are getting rejected and rejected. Females are getting better and better offers as the algorithm progressed. It looks a bit unfair, and the answer is yes, it's completely unfair because this algorithm is actually will guarantee that among all the possible stable marriages, every male will get the best female that he can get in any stable world, and if any female will get the worst male she will get in any stable world. So no, it's a terrible algorithm. Now, we presented one stable matching algorithm that produced one possible matching. Either other ways, or could it be that there are more than one stable marriages? Can we find them? Answer, yes, absolutely. Just switch the rules of the males and the females, and everything that we said about the proof is still holds. Right? We are still sure that the output would be stable. Okay, so we'll leave it at this point. I'll ask you a few questions about it in the homework. Quick question also in the homework, but just to check. We said that there might be n-square many rejections. That would be in the worst case. What is a minimum number of rejections that could be? How could it be that there are n-square many rejections? It will not be exactly n-square, but as you can guess, one person was rejected by almost everybody, another person was rejected by almost everybody, another male was rejected by almost everybody, and so on. And you can show, actually you will have to show in the homework, that it might lead to n-square time many rejections. My question is, what is a scenario at which we have the fewest number of rejections? And a few of you already said, and what's the input? A few of you already said it's possible that there are 0 rejections. That's correct. How could it be? Like, what's the input that would lead to this case? What's the preference list? Absolutely. Correct again, Diego. The moment you'll say that the first choice of all the males, that no two males have the same first choice, then each male makes his first proposal to different females, none get rejected, and after one day, everybody got married. So yeah, that's exactly the case where there are no rejection at all. Okay. When Ryan, I'm not sure that I understand your comment. Are we saying the same thing? That the first choice of all the males are different. No two males have the same first choice. Ryan, I didn't understand the comment exactly.
I think he's saying they are each other's first choice.
Yeah. Okay. So yes. Now, it's as I mentioned last meeting. This algorithm gave Shapley his Nobel Prize together with other works about reasons of stability. Stability, like in Nash equilibrium, that if somebody loses, that it's stability because any changes somebody will lose from it. Very high level hand waving. There are many algorithms that are variants of these algorithms that both suggest more fairness and tries to optimize different criteria, of course. And there are as well there are as well algorithms that handles, of course, the case of what is referring the algorithmic literature as a roommate problem, where you have n people, each one gave a full ranking of each one of the other people, and we are trying to pair them in any way such that there will not be any rogue couples. You can still define rogue couples, and the algorithms that addresses it, this problem by itself is NP-hard. So that's why I don't describe an algorithm for this case. And of course, my interest in it is, of course, when there are geometric meanings to the preference or the location of the people, and can we find, or we have find better algorithms in certain cases. Okay, let's move to skip list. I'm very happy to know that you already know skip list, so hopefully I will not spend too much time about it, both for the case that I'll be able to tell you something new. I'll still go over it, but probably spend less time than usual. For the one of you that have covered it in 345. Okay, before I want water. I'll be right back. I played with a setting in Twitch that I also broadcasted to. I think that there is a place for the mediator in Twitch if anybody is playing to misbehave. Okay. What is a singly connected linked list? Refresh your memory. I hope that you all know it. Singly connected. Yeah. Singly connected linked list, a set of elements. Each one has a pointer to the next element. There is one pointer to the very first element, and the last one maybe points to null, maybe points to what we'll call a essential element. You'll see an example in a second. Just if you are not used, if you didn't take C for whatever reason, you're not used to pointers at all. It's a bit under the rug if you know Java. So you can think about it as just an array of elements where every cell in this array has a key and has the index of the next element. That is, if my first element is A, the first element in the list, say it sits in index 106, and it stores as a key the A from here, and it tells us that the next element sits in the array at address 110. And in 110 I'll find B, and it will tell me that the next one is in 118 at C, and C will say that the next is D at address 104, and D will say the next one is, say, null. I'm the last element of the list. Okay, and somewhere we keep the address of the very first element. Okay, so we have cells each in the memory, each one with a key and a pointer to the next cell. A pointer, as you know, just an address to some other cell in the memory, or an address in the hard drive or in the SSD. Doesn't have to be in the main memory. There is a head pointing to the null. There is and the main thing about singly connected linked list, it's very unpleasant, very non-efficient to move backward or to find the element just before you. But however, it's very easy to move from an element to the element next in the list. Okay. Doubly connected edge list, each element points to the next one and to the element just before. So in particular, if we want to insert element in some random place, it's much easier because we can find who is before it and who is after it. So some operations are easier to do if in doubly connected edge list, linked list. How do I search for a key X in just a sorted linked list? I want the keys to be sorted. All my list will be sorted from now on. And I'll also keep two extra elements in the skip list that takes tiny little bit of more memory, but in return saves the complexity of the code by quite a headache that we are missing. These elements would be the element at the end which has key equal infinity, and the very first element of the list which has the key minus infinity. So these are not data items, they are just special characters. Every language has max int and min int, max float, min float, and that's what you're using as a min infinity and infinity at the beginning, at the end. How do I find an element? Here in a very basic C, I'll want to search for an element X. I'll set a pointer P that will point to the head of X, and at each moment I'm looking one element ahead of me and asking what is a key, not of where the pointer P is pointing to, but of the next key. And as long as this next element is smaller than x, I'm moving forward. So if I'm looking for 71, then what the code will do is it will put the pointer p on minus infinity. It will say the next element, p next key, is 7. 7 is still smaller than 71. Then I'll do p equals p next. Move p from the minus infinity to 7, and now check if 14 is still smaller than 71, and so on. So if I'm actually looking for 71, I'll end up when I'm pointing to 37. If I'm looking for 40, which is not in the list, I'm still ending at 37, both cases. So in this pseudocode, I'm not returning the element with x, but I'm returning the predecessor of x. That is, formally, it's the largest key, which is strictly smaller than x. In a sorted list, it's just the one coming right before x. And as I said, minus infinity and infinity are not real keys. And some you can replace it, actually the other way around. You could have replaced it by, if all you want to know is to find the element with x, you could have asked if p key is already smaller than x or not. Why do I care about the infinity and the minus infinity? Where does it save such a headache? Is if I wouldn't have the infinity over there and p would have looked at the last element, then trying to call for p next would have caused a crash in ANSI C. Or it's an ugly bug that to avoid it, you have to insert another check here. Is p already points to null or not, and not to proceed if this is the case. So the infinity at the end save us the one if that would have complicated the code, as well as simplified the insert and delete. As we'll see in a second, without the infinity minus infinity, we would have to handle this as special cases, inserting the very first element or inserting the very last element. Inserting a key into this sorted linked list, if I want to insert 35, what I do is I'll perform firing of 35, and I'm getting as an answer a pointer to the element which is a predecessor of 35. Predecessor of 35 meaning the largest element, which is still strictly smaller than 35, 32 in this case. If you follow basic C, at this moment you're asking for a new cell P1. You can just use new in C++ or Java or any normal language. In basic C, you will use malloc. And P, you want to insert 35, put 35 over here as a new element, arrange the next pointer of this element to point to P next, which is the address of this element, and now P itself next goes to point on 35. Okay, everybody feels hopefully familiar with this, with or without C. Same goes if you just implement it in an array, same goes if you implement it with references. Note that because of the infinity, it's okay to insert, if I would want to insert 118 right now, I don't have an issue. It's the same code would still satisfy it. If I want to insert 6, the same code would satisfy it. I don't need any special cases for the first and the last element, so my code is much more compact and much faster. You are saving a few ifs in the cost of slightly increasing the memory. Okay, deleting an element even easier. I want to delete 37, so I do find 37, which as before returns the address of the predecessor, 32 in this case. And what you're doing is just telling the next of 32 to go and point to the next of 32 of 37. The next of 32, which is just jumping over 37, implying that 37 is not in the list anymore. In C, you would expect it to do some garbage collection if you are good citizens. If you not as not, then however, 37 stops being in the list at this moment. Questions? Good. Let's start speaking about skip list. I'll give you a set of rules. Those of you that know skip lists, you'll see the light immediately. Those that don't know skip list, these rules would look very awkward at first gaze. Here is how a skip list looks like. So skip list consists of several levels. This will be one level. I'll call it the lowest level, level 1 in my slides. This will be level 1. Level 2. Level 3, maybe I have fewer levels, maybe I have more levels, doesn't matter. I have a top register, a pointer called top that points to the very first element at the uppermost level. Each level by itself is sorted. That is, if I'm going through all the elements in the lowest level, 7 is smaller than 14, smaller than 21, smaller than 32, and so on. Same goes for level 2, 7 is smaller than 21. And same goes for each and every level. Another rule, if a key X appears in some level I, then it must also appear in all the levels which are below I. 21 appears in level 3, then it must appear also in level 2, and it must appear also in the base level, level 1. Now 14 appears only in the lowermost level, doesn't appear in level 2, which implies it cannot appear in level 3. You don't jump levels. Okay, if it would have appeared in level 3, then 14 must have appeared in level 2 as well. First element in each level has this key minus infinity, just as normal sorted link list. As we said, every level by itself is a linked list. First element in the upper level is the one pointed by top, so you can start searching somebody in the list. Last element has plus infinity in each one of the levels. And if you look at one of the keys, it points, we distinguish between key and element. Key and elements are not the same thing. An element is this disk over here. A key is a key of a number, student ID. So I have a few elements that all contains the same key, 21, and they need to point to each other. From the uppermost, I need to go to the one below, I need to be able to go to the one below, and so on. More rules. Each element in level larger than 1 points, it has a down pointer to the element with the very same key just below it. This 21 has a down pointer to this 21 that has a down pointer to this 21. This element also have a down pointer, except that it points to null. That's how you know that it's the lowermost level. Its down pointer is pointing to null. Null is a constant, you know, 0 or -1, whatever it is. You don't use the exact value, you use a constant null. And at some point I want to keep a counter that will tell me how many levels do I have. Here is an empty skip list. That's how a skip list that has no data items looks like. Only the minus infinity and the infinities are not real data. They are there because to make our search faster. So no data points over here. However, an empty skip list might have more than one level. That's legit. But they are all infinity or not. Here is how I'm searching for an element X in the skip list. I'll start where a pointer P is the top, the minus infinity at the uppermost level. And while 1, that's not how I'm exiting the loop, as long as I'm not done with the loop, look at this line. My goal here is in the very top level, in the highermost level, I want to go as much to the right as possible, provided that the next element is not larger than x. I'm always careful that my next element is not larger than x, but given this in mind, I'll try to move as much to the right as possible. And I'll always try to keep to the level I am on for as long as possible. I'll move down in the skip list only if I don't have any other choice. So as long as the key of the next element is still smaller than x, do p equals p next. That is, move one element to the right, the next is always to the right. At this moment, you cannot move to the right anymore because then you'll exceed x. And as we said, in a linked list, you cannot move backward. You cannot move to the left. So you are only allowed to move either to the right or down. So if P down, if you are already in the lowermost level and you cannot move to the right, at this moment return P. Otherwise, if P has a down pointer that is not null, just move downward. And at this point, the loop will start again by go to the right as much as possible. Let's see an example. It will make much more sense than all my explanation. Here I'm performing find of 117. Find of 117 will start at the top. X is 117, trying to go to the right. Is it safe to move to the right? Yes, because the next element is 21, still smaller than 117. Fine. Still safe to go to the right. Is the next element smaller than 117? No, it's actually infinity, so it's time to go down. Now is the next element smaller than 117? Yes, move to the right. You cannot move to the right once again. Go down, move to the right until you find the predecessor of 117. You cannot move to the right anymore at this point because this element is too large, and you cannot go down because this is a null pointer. So at this moment, you're pointing with P on this element and you're exiting. So that's how the search looks like. So again, the rule is try to stay in the same level as long as possible. Why? What's happening at the uppermost level? So think about it as a station of a very slow train. These are the street numbers in Manhattan, and think about it as a slow train that stops at all these stations versus a fast train that stops only at 21st Street, 37th Street, and that's the only station. What would you do? You will try to use the fast train as long as possible. Let's think about it. Because it moves much faster at this point, you'll move into the mid-fast train, mediocre train, move a bit to the right, and only then you'll move to the very slow train that stops at all stations. Or putting it in other words, what happened in a search tree? Let's see the analogous to a normal search tree. So I have 17, and I have a bunch of elements in the right subtree and a bunch of elements in the left subtree, and here sits 100, and I want to find 100 in the search tree. And one way to do it is to go through all the elements, one element at a time, from the smallest one until you'll get to 100. I can keep all the elements sorted and just wait until I'll get to 100. However, what the skip list or what the search tree enables me to do is to say, hey, search tree, at the root there is 17, and which tells me that everybody over here is smaller than 17, which tells me that if I'll go, there is no need to search for 100 in the left subtree, so let's just let's skip over everybody in the left subtree and go immediately to search in the right subtree. And the skip list enjoys the same philosophy. It tells us if you're looking for somebody who is larger than 21, then everybody in this portion of the skip list is smaller or equal than 21. Let's jump over it. Right? You want to look for 115. Let's do a skip over everybody that we could, as long as we can do these skips. So another way to think about the levels is that in level 1, all the keys are sorted. That's the main level. The level 2 is a subset of the elements that is in level 1. Level 3 is a subset of the subsets of elements which is on level 1, and so on. We are refining subsets. We keep picking elements, subset of the elements that we pick in the lowest level. So it's kind of level of details that you see in graphics. Let me tell you about a perfect skip list. Perfect skip list is a unicorn. Most skip lists that you'll see don't look perfect. So, and it's my terminology. Didn't see it in other textbook. So I'll tell you that a skip list is perfect if between every two consecutive keys of level I, no matter what is I, there is exactly one key at level I minus 1. Let's explain. Between two consecutive keys at the lowermost level, I have, let's start from the 4. Let's look at the 4 and 7. There are two keys. One of them will be in level 2. The next two keys, one of them will be in level 2. Next two keys, one of them will be in level 2, and so on. Out of every two keys, there is one element that is popped up. In other words, every second element is promoted. 4 is not promoted to level 2, 7 is promoted. 14 is not promoted, 21 is promoted, and so on. Yes, no, yes, no. That's how I created level 2. Next, how do I create level 3? I'll apply the same rule of level 2. Meaning, I'll decide the minus infinity promoted, 7 not promoted, 21 promoted, 37 not promoted, 71 promoted, and infinity promoted because everybody's in there. It's exceptional. It's in level. All the levels have infinity at the end. Okay, and that's I'll call perfect skip list, and the reason that I'm mentioning it is a few reasons. One reason is it will be very easy to analyze the running time on a perfect skip list. It's much harder on a real skip list. And secondly, if you do use skip list and from time to time its performances are degrading and you want to rebalance the skip list, then what I actually describe right now is a very practical algorithm, and it has linear time. The algorithm that says I'll start from the lowermost level and alternate elements yes, no to be on the level above it or not, it's a very practical way, and it's and it is a very practical algorithm to rebalance the whole skip list if its performances are degrading. Now, as you'll see, there is some waste of memories that happens here, but that's kind of unavoidable. But let's understand what is unavoidable. Let's say that I want a data structure that will support find operation. Only if I have data structure that needs to be enables me to perform find of key operation. What's your option? if all you need is find of key and don't care much about how much time it takes to prepare the data structure, then your options are hash table. We'll talk a lot about hash table. It's fantastic when it works, but it makes assumption about the keys. And hash table doesn't allows you performing operation such as a report x1 of x2, which needs to tell me print all keys which are large or equal than x1 but smaller or equal than x2. So hash table doesn't tell me anything about who is in the range, or similarly it doesn't tell me about count. Count of x1 and x2, which is an operation that should report how many are in the range x1 and x2. And it doesn't keep any order. So the count operation that tells me how many keys do you have between x1 and x2. Of course, you can, to do the count, you can go to the report and apply the report operation, but actually you can do much faster if you just want statistics about all these elements. Hash table is very sensitive to errors about if I'm looking for somebody whose height is about 6 feet, but I'm not exactly sure, then it's very likely that you wouldn't find this element in the hash table. So what other data structure are you familiar with? What's the best data structure if I want to support, say, find operation and I want to prepare the data structure ahead of time? What's the best you can do? You can do better than red black tree. Red black tree is not a bad answer, but you can do better. You can do better than B trees. B trees will be fantastic as well as red black, but the moment that I'll say that you also need your data structure to be dynamic, if I want to support insert and delete and find in a reasonable time, then B trees and 2-3 trees and skip list are doing quite fine. Hash table will support all these operations, but doesn't support the range and counts and anything that involved order of elements. What happens if I just want to support find operation and I don't care about the dynamic aspect? You cannot beat sorted array. It's optimal. You don't waste any time. You don't space any space. It's as compact as you can without real compression. You can do binary search. Binary search takes log to the base 2 of n, which is optimum. It's red, black, B trees, all these guys supports constant order of log n. It's no more than 3, not more than 5 times log n, but a constant times log n, which is a price that you have to pay if you want to also support insert and delete. But sorted array should be your answer to go if you don't need to insert or delete elements frequently. Anything else needs to trade somehow search time and memory. Right? You're not anymore in the log n search time, you're in the order of log n, constant times log n. And secondly, you need more memory to keep the color of the node, for example, or the height in an AVL tree, or you'll have to have some extra memory, hopefully not too much, to arrange more pointers, just as in the skip list. Right? Array is very bad if you want to insert elements. If I want to insert an element into a sorted array, as opposed to what Java or Python might make you think, what you actually need to do is to go to the array and now shift everybody to one side to make room for an element to be inserted. It's a very inefficient operation. If you want to not to go through a linear time operation for insert, you need to allow pointers and dynamic memory allocation, which in turns going back to the comments in the chat, that yes, the skip list does waste some memory. A key is sorted several times, maybe a lot. We will talk about how much memory am I wasting, and I'll try to convince you that it's kind of a roulette that you are hoping that will work well, but the chances, the odds are definitely on your side, and you're very likely to waste very little. But that will require some proof. So back to our perfect skip list. What would be the search time in a perfect skip list that contains n elements?
I'll just log in.
It will be exactly log n, because how many levels do I have in a perfect skip list? I start from n keys at the lowest level. Level above it there is we have n elements in the lowest. Level above it there is n half many elements. Level above it there is n over 4, n over 8. So after log n many levels, I'm done. I cannot continue any further. What would be the search time? Well, in a perfect skip list, it needs a proof, but you'll see that you never need to go to the right more than 2 elements. In a perfect skip list, you'll never have to go to the right more than 2 elements. Why? Why wouldn't I go to the 21 and then to the 71 and then to somebody after it? It's because if I'm looking for somebody that is larger than 71, then I would have stayed more in the upper level and go to the 71 over here, because my jumps are larger. So it's a hand wave, but I'll never waste more than 2 elements per level, and there are log n levels, hence the search takes log n. Search takes order log n. What about the space? How much memory do I spend? If I have n keys. Order of n log n is correct, is a correct bound, but it's correct bound in the sense that we are in a balloon. It's correct, but it's not a tight bound. Order of log n is correct. Let's count. How much memory do I spend? Let's start from the lowermost level. I am spending n elements in the lowermost level. One level above it, I'm spending n over 2. One level above it, I'm spending n over 4. N over 8 plus, and I do stop at some point, but this sum that, as I mentioned, will escort us many times in this course, what's written right here? This is small or equal than n times 1 plus half plus 1 over 4 plus 1 over 8. And why is it smaller? Then I'll just keep adding elements all the way to infinity, very infinitesimally small elements, and then I'm sure that this sum equals exactly to 2. 1 plus half plus quarter plus 1 over 8 plus all the way to infinity equals exactly 2, implying that the memory that I'm wasting is just n times 2. So see what I got. Instead of sorting just n memory, I'm spending 2n, but the search time went down from being being linear, that I should have done in a linked list without the skips. I'm getting down to log n time. Okay, so yeah, we are trading memory and space. Okay, but as I said, perfect skip lists are unicorns. Not most of them are not. Yeah, searching a skip list we already mentioned. Just a word. What should I do if I look for 71? Say, in a perfect or non-perfect doesn't matter. And let's say I'm looking for 71. I found it right over here. And should I stop or should I go all the way to the very bottom? And the question is depending on the one you're asking. Maybe you're asking, you'll find 71 just to know if you have a student with this ID in the university, and the moment that you discover that yes, the search is over. And so you can stop right here. Most commonly, you want to find 71 because you want to access the auxiliary data, the satellite data. Every key comes with the student record, student address, a lot of other things that are related to the student ID, and you definitely don't want to keep all the data, all the large auxiliary data, the whole student record, multiple times. You need to store it either in auxiliary hard drive, auxiliary disk, or similarly to B+3, if you've mentioned, you'll store it only with the lowermost level. Only the lowermost node will be of a different type, and it can store auxiliary data with it, while the other element just tells you, yes, I found 71, now you have to go down, but the rest of the data is all the way down. So that's about where should we stop. Now, let's study how to insert a new element X into the skip list. And I'll give you my version of the code. So we first pick a magic number K. And K will tell us in how many levels this new element X is going to participate. We want the skip list to be balanced in some way. There are various considerations. I want to pick K in how many levels X, the new element, is going to participate. That was the hard part. Now when I know what is K, how many levels X is going to participate, I'm performing find of X, find of 119 at this moment. In this example, let's say that K is, I'll remember in a second. However, as I'm going down, I notice every time that I am not turning to the right but going down, it is a suspicious element. And now if K participates, K is 2, meaning 119 participate only in the lowest 2 levels, then every time that I'm in level 2 or level 1 and I see where 119 should appear because it's just the element at which I turned down or I stopped the search, and I add 119. How? Exactly the same way that you did it in a linked list. That's why I went through all this gymnastic at the beginning of this lecture about how do you do it in linked list. Skip list is just barely, just minimally more complicated than a linked list, in the sense that I just have several linked lists, and in each one I'll insert 119. And oh, there is this hairy part of I need to pick K and decide what is K, but after that at each level that 119 is inserted, I'll insert it just as a linked list. It's way simpler than red-black trees or AVL trees with various types of rotation and various types of cases. No cases at all. But now let's see how do I actually insert, and I'll be there in 30 seconds. Here's a case of inserting into a few levels. We'll mention it in the next lecture. Let's see the algorithm for determining K, in how many levels X is going to participate. And what you need to decide in how many level X is going to participate, you need a coin. You don't look at the skip list at all. You don't look at the data at all. You don't look at where X is in the skip list. What you're doing is you're looking at a coin, tossing, and you decide X is going to participate in level 1 for sure. I'll toss a coin, and if it happens to be face, then it will also participate in level 2. If it happens to be a tail, it stays only in level 1. If it's face, it will go to level 2, and then I'll toss the coin again, and if it's face, it will participate in level 3. And I toss again the coin again, and if it's face, it will participate in higher and higher level. But the moment that I got a tail, I stop. No more levels. How do I do it in my computer? I'll decide about a function that I'll call our random number that returns 0 or 1. And I'll call our random number, I'll start with k is equal 1, and if our random returns true, do k++ and repeat this experiment. Happens to be 1 again, do k++, repeat this experiment. You stop the moment that there are no more, that you got false the first time, and that's the whole insert algorithm. No very details. It's 20 minutes programming for most of you. Extremely simple and get the same or much better performances than AVL or red-black or B-trees in many cases. Perfect. See you next Tuesday.